Hello calculus class. Today we're going to look at our first remainder theorem, which is going to be a continuing theme as we try to approximate the value or the convergent value of series that turn out to be convergent. Like I said in previous lectures, geometric series are pretty special in that it's really easy to compute their convergence if they do converge if r is less than 1. But for other kinds of series, that's much more difficult, so we'll be approximating their convergent values in most of the remaining sections this year. So the first thing I wanted you to look at was go ahead and click this link on the remainder theorem for the integral test, because that's what we need to do for section 9.3. So I think this has, besides just the integral test, this link has quite a bit of information that's going to be useful to you, so you might come back to it because it does remainder for not just the integral test, but for some of the other tests we'll be using as well. So don't forget about this link if you're getting lost. So you can read through this carefully. That's something I really would like you to do. But the idea is you can compute the remainder of a series pretty simply. So if you have a series going from 1 to infinity, it's of course plausible to stop at some n and then continue from n plus 1 out to infinity. So that's what this does, is it just stops somewhere. So the real sum of the series is of course going to be this, so we're going to call that small s here. I'd usually call it capital S, but whatever. And then this place we stop to is the sum of the first n terms, like that index says right there, if we zoom in a little bit. Yeah. Okay, so that's s sub n, and then this is what's left from that spot we stopped at, n, out to infinity, so we're going to call that r sub n for the remainder. So you can of course solve that little equation for the remainder by going minus s sub n on the other side, and the remainder is this ultimate sum of the series minus the sum of the first n terms. That's what this is. So how do you develop a theorem to pretty much estimate the convergent value of a series from this? Well, it's pretty simple. So let's go down and look at a function curve and think about it. So r sub n, you can see here, is just going to be the sum of the terms from n plus 1 out to infinity. So let's think about an arbitrary curve here, where this one looks like it's concave up and decreasing. Most series we're going to consider, if they're convergent, will be decreasing, right? They can't be increasing or they're going to diverge. So this is a pretty good example of what pretty much any series is going to look like. So if you think about the function from some spot n plus 1, because remember we're just talking about the remainder, we're just going from the n plus 1 stopping spot that we decided on out to infinity to get the remainder. Then you've got term n plus 1, term n plus 2, term n plus 3, and so forth. So the article says here, we can see that the remainder r sub n is the area estimation, and it will overestimate the exact area. So it's going to overestimate you here because you're going to get these little extra pieces above that. So r sub n is going to be greater than or equal to the actual integral under the function curve from n plus 1 to infinity. So now let's go back and look at, instead of n plus 1, let's look at starting at n. So if you look at starting at n, you can see something else. It says again, we can see the remainder r sub n is, again, this. We can see that the remainder is r sub n, and it is again this estimation, and in this case it will underestimate the area if we go and look at it like this. So this leads to the following inequality. So if we look at the nth term from n to infinity, then r sub n is going to be less than that. It's going to be less than that because of the underestimate here. It's going to be more than n plus 1 to infinity because of the overestimate here. So in other words, r sub n is trapped between those two values. So in other words, if you find those two integrals from n to infinity and from n plus 1 to infinity, of course n to infinity is going to be more than n plus 1 to infinity. It's going to have more value to it, if you will, because you're starting back to the left further. That's going to be larger than this, and r sub n is also going to be trapped between those two continuous quantities. R sub n is of course a discrete quantity, it's one exact value. And that's what we're trying to estimate. If we can estimate the remainder, we can also estimate the sum that the series converges to, using where the remainder came from. Let's remember that the remainder came from the sum is the first n terms plus the remaining terms after that. So what you can basically do is just put this together with this, and solve for s, and you can get a bracket on s. Don't make this hard, it's very easy algebra, it just kind of looks ugly, so I'm not going to write it down. But basically you can use this to not estimate only the remainder, but you can use it to estimate the sum, s. So s then is between the first n subterms plus the integral from n plus 1 to infinity. It's bigger than that. and it's smaller than the first n sub n terms plus the integral from n to infinity, which is a larger integral than this integral. So we know that s is trapped between those two things. This is the remainder theorem for the integral test because, of course, it uses integrals on both sides. So let's go and do one of the examples in your assignment. So in your assignment, I think one of the examples, this is number 65. I guess I'll put that in here, number 65. Number 65 says to estimate the convergence of the series below using 4 terms. So the first thing we want to do is get the first 4 terms, or s sub 4. That's like s sub n, what we were looking at a second ago. So s sub 4 is going to be 1 divided by e for this guy, plus 2 divided by e to the 4th power, I think. Right? You can just keep plugging in it. So I plugged in 1, I got that. Plugged in 2, I got e to the negative 4, that goes on the bottom, 2 over e to the negative 4. Get me? Okay. So we're going to keep going in like fashion. This is going to be e to the 9th. And then we're going to have 4 over e to the 16th. So I'm going to put that in my calculator. And my calculator is going to, not infinity. My calculator is going to tell me it's approximately equal to 0.4049. Okay, so that's the first thing. Now we need to remember that s is going to be bracketed between that and our 2 integrals. So let's write that out. So s sub 4 plus the integral, you have to bear with me here, the integral from 5 to infinity of the function x e to the negative x squared dx. That's going to be the lower bound of our approximation. It's going to be less than or equal to the sum that we're looking for when trying to estimate. And the upper bound is going to be pretty much exactly the same thing, so I'm just going to copy and paste. Going to be s sub 4 plus, and then we want the larger integral, which is going to go from 4 all the way out to infinity instead of only from 5 to infinity. So the true sum that we're trying to approximate is between those two things. So all you need to do now is evaluate those two improper integrals from 5 to infinity and 4 to infinity, and you'll have your estimation. So that's all I'm going to do. So on my next line, I'm going to say s sub 4 is 0.40. You know what? I'm just going to leave it as s sub 4 for now. Plus, and I'll even write a little bit of the integral here. So that integral is negative 1/2. So we're going to go plus, it's just negative 1/2. So negative 1/2. And then we're going to go, the antiderivative comes out to be negative 1/2 e to the negative x squared. I'll leave that for you to show yourself. So that's going to be 1 divided by e, and that e is going to be raised to the infinity squared. Crazy. Minus 1 divided by, and now I'll plug in the 5, so it's going to be e raised, 5 squared is 25. So there we go. So we're going to have that, and then we're going to have less than or equal to the thing we're trying to estimate, and the upper bound on the thing we're trying to estimate is going to be really similar, so I'm just going to borrow this stuff, paste it over here. So we're going to have the antiderivative still the same, except here instead of e to the 25th, I'm going to have 16. And there you go. So the thing we're trying to estimate is going to be bounded by those two things. I just go to my calculator and get some more specifics. So s sub 4 we said was 0.4049, about. And then when I put this in my calculator over here, 1 over e to the 1 over infinity squared is of course 0. This of course goes to 0. And this is so close to 0 that it really didn't add anything. In fact, I added a little bit. It, minus. You've got minus times minus going on here. This was really, really tiny potatoes here. 944 times 10 raised to the negative 12th power. That's not going to affect anything for the estimation. Remember, we always in AP land we only want thousands rounding, so that's going to be pretty much plus 0 there for us. And then on the other side we have 0.4049 plus, I think it was a little bit more significant here. I got 5.6, 5.627.
Football banquet will be tonight at 7 o'clock.
10.
All football players, reminder, football banquet is tonight at 7 o'clock.
8th power So I mean, this is pretty negligible, but you can see that we've got a really good estimate for this series. We've got a really, let me space this out a little bit here so you can see a little better. We've got a really good estimate for this series because these are both really negligible additions that we're adding here. In fact, let's just really show it in one last step before we sign off in this example. So 4049 plus point. If that's 10 to the 11th power, then we got 1, 2, 3. 12th power is 11 zeros. 4, 5, 6, 7, 8, 9, 10, 11, 6, 9, 4, 4. So S is between that and 0.4049 plus point. 8th power is 7 zeros. 1, 2, 3, 4, 5, 6, 7, 5, 6, 2, 7, 2, 7. So you can see that we have a really tight estimate for what this integral actually converges to. You'd have to show it converges with the integral test, but this is showing what it converges to within a nice margin of error. Alright, so there's your first remainder theorem in series. We'll definitely come back to that. Remember that link will work and has some great examples for other tests besides just the integral test. I'll see you next time.